Alright, so the purpose of our video today is to talk about predicting shapes of molecules, and we'll talk about the VSEPR theory, which helps us to explain this. The reason why this matters is because the shape of molecule is going to impact maybe how it's absorbed by the body. If it's a drug or something, certain shapes are going to be absorbed differently than other shapes. It helps to explain to us interactions between different molecules. So it helps us to explain like the properties of water or the properties of gases. And so the shape and determining what the shape is very important for us. Okay, so when we look at shapes, we talk about the VSEPR theory, and this is the valence shell electron pair repulsion, and it's looking at how electrons interact in space and how that impacts the shape of a molecule. We will use this PhET simulation here to look at that, but the other link on there is also a really great resource. They have some videos and they have a chart of all of the different shapes, and it's a really great resource if you need some extra assistance as we move forward. So looking at the VSEPR theory, we're looking at how do we predict molecule shapes based upon the idea that electrons repel one another. So whenever we look at this, we're looking at lone pairs of electrons like we drew in our Lewis structures. We're looking at single bonds and multiple bonds. And electron groups are going to strive to be as far away from one another as possible, which kind of confirms what we see with the Pauli exclusion principle with orbital diagrams, which is that electrons of the same spin in the same orbital would repel one another. So electrons want to be as far away as possible, but then also still be close to the nucleus. So with the VSEPR theory, we talk about regions of electron density. This is going to be areas where electrons can be found around the central atom, so that can be bonds or lone pairs of electrons. And both the unshared pairs and the bonding pairs will play a big role in the shape of a molecule. So a few terms to be familiar with. We talk about electron domains. So this is the total number of areas of bonding and unpaired electrons that are around the central atom. We talk about bonding domains, so this is the total number of bonds around an atom. Each type of bond counts as one, so even if it's a double bond, it still only counts as one bonding domain. We also talk about non-bonding pairs or lone pairs of electrons, and these will just be the number of non-bonded electron pairs around the central atom. So electron domains will be the total, and then we will classify those kind of within by talking about specifically how many bonds are around it, and then specifically how many lone pairs are around it. This helps us whenever we're defining electron geometry and molecular geometry. So electron geometry is going to be the arrangement of the electron groups or the electron domains. So this will be how many areas of electrons are there around the central atom. So this doesn't really take into account, this takes into account everything bonding and non-bonding electrons. The molecular geometry is really the shape that we'll see. It's going to be the arrangement of the atoms. So wherever the atoms are in space, this is what we call the molecular geometry. The molecular geometry is impacted by where all of the electrons are, even if they're not bonds. And so electron and molecular geometry are very closely related to one another. For electron geometry, here are a few examples. So this is going to be based upon the number of electron domains, which includes the bonded and non-bonded pairs. And so if we have two electron domains, then the shape will be linear, or the electron geometry will be linear. And we talk about bond angles, and we'll look at this a little bit more later. But remember that whenever we look at this, we're looking in three-dimensional space. So if we have three bonding domains, then how far apart could they be in 3D space? If we're thinking of a sphere, they could be 120 degrees apart, and we'll call this trigonal planar. Whenever we have four electron domains, then we call it tetrahedral. And if you think about how far apart can it be kind of in a sphere, it's not going to be 90 degrees, it's going to be 109.5. Now, these are all ideal bond angles, and what we'll find is that they're not going to be maybe exactly like that in nature, but they'll be somewhere close. Okay, you can also see what it's called with 5, we call it trigonal bipyramidal, and then with 6, we call it octahedral. Now, with molecular geometries, what we find is that molecular geometries are related to electron geometries. So this will be based upon where the atoms actually are, which depends upon the bonding domains, but it's impacted by the electron domains. So what this picture is showing is it's showing what does the geometry look like if all of the electron domains also have atoms. And so this is what we looked at with the electron geometry. So we have linear, trigonal planar, tetrahedral, bipyramidal, and octahedral. And this electron pair geometry is just showing you where all of the electrons would be in space. Whenever we have molecular geometry, sometimes it's the same as this spatial geometry. So if you have in this trigonal planar, you have 3 atoms that are around the central one, just like this, well then the molecular geometry is also trigonal planar. But if one of the electron domains is not filled, then that electron domain is still impacting what the shape is going to be, but the actual arrangement of atoms, where these green ones are, is going to then be called bent. Okay? Same thing is true for tetrahedral. So if you have 4 atoms around the central atom and there's no other extra electron domains, then it will be also tetrahedral. But if you have 3 and there's a lone pair of electrons, then it makes it trigonal pyramidal. If you have 2 lone and 2 filled, then it would be bent, like this would be water. Okay? Whenever we look at electron and molecular geometry, if all electron groups are shared around the central atom, then the electron and molecular geometry is the same. So this means if they're all bonded around the central atom, then the electron and molecular geometry will be the same. So that would be here, tetrahedral. If these are all atoms that are bonded, then that would be also tetrahedral molecular geometry. However, if there's lone pairs, like if this green one up here was a lone pair, then the electron geometry would be tetrahedral, but the molecular geometry, or the shape which we actually see, would be pyramidal. Here's another table from your book that explains this. It looks at linear geometry, trigonal planar if you have 0 lone pairs or 1 lone pair, and then tetrahedral if you have 0, 1, or 2 lone pairs. Here's some more resources that you can use. This is showing the same thing as before, just making sure that you're familiar with and that you understand that electron geometry is where the electrons actually, and molecular geometry refers to where the atoms are. So whenever we've looked at Lewis structures in the past, we just focused on the general arrangement of atoms around the molecule. Now with the VSEPR theory and kind of drawing, we'll focus on the 3D shape of the molecule. So first, we'll determine the shape by drawing the Lewis structure, and then we'll redraw the Lewis structure to show some bond positions. We generally keep the unshared pairs on the same side of the molecule, and then unshared pairs kind of are moving around where the shared pairs are, which is what we talked about with VSEPR. So here are some of the things. You can go ahead and draw these down just so you're familiar, but something like linear, the bond would be in the plane of the paper. Trigonal planar, everything's all in the same plane. Because it's planar. And so the ones that we have to think about would be something like tetrahedral, where if you had this molecule, you would have 2 of the bonds that would be in the same plane, and then you'd have 1 atom going back into the paper, and then 1 atom coming out towards you. And the same thing for trigonal planar. We would draw this as getting rid of that extra one kind of going up, and so you'd have 1 going back into the paper, 1 towards you, and then 1 in the plane of the paper. And we'll look at this a little bit more as we go through some examples. So let me show you a little bit about what I mean with drawing the shapes. And so if we reset this, so if we have linear, what we see is that everything is in the plane of the screen. And so the bond angle would be 180. We would call this linear and linear for our geometries. If we add another bond, notice that we still stay in the same plane, or that we can all be in the same plane of the paper. So we would just draw a single line. Of course, you could turn it around, and you could have 2 coming out towards you and 1 going into the screen, or you could change it and move it around, but the easiest way to draw a trigonal planar would be that it's in the plane of the paper. And when you add another bond, now you have tetrahedral. So you have 1 going up, 1 coming out towards you, and 2 going back, so you could draw it that way, or you can bring it like this, where now this one and this one are generally in the same plane, and then you have 1 going back into the screen and 1 coming out. And so we'll kind of focus on how we would draw that. Now, if we replaced one of these with a lone pair, so let me eliminate one of those. So if we replace one of these with a lone pair, Same thing, so this is tetrahedral for the electron geometry, and you have generally one bond that would be in the same plane as that electron, and then one going in and one coming out towards you.